Okay, so in this video, I'm going to go through continuity, really part 2, but assignment number 8. Okay, so the first problem is we have a graph of a function f, and classify the definition of, using the definition of continuity, explain why f is not continuous at x equals 2, or not continuous at x equals 2. But our function is continuous at x equals 2. So I think that should have been, probably as I'm looking at it, let's explain why it is continuous at 2. So that's a little typographical error there. And we're not going to do that because it is continuous at 2. So we're going to do our strategy of sentence starters, the function value, the limit value, and the comparison. So f at 2 here is 2. We can see right here that it is 2. And obviously the behavior from the left and the right of 2 is 2. So f at 2 does equal that limit as x approaches 2 of f. In part B, how about 3.5? We take that about to be 3.5. So we do again, f at 3.5. We're looking for the closed circle now. We've got it probably at about 2.5, that is. So here's 3.5 up and over is about 2.5. But definitely we don't have a limit. So as x approaches 3.5 of f, that does not exist. In fact, we have a jump discontinuity there. And then I did say down here 1, so at x equals 1, it is continuous because f at 1 does equal 1. The limit as x approaches 1 of f is 1. And we need to say that f at 1 equals limit as x approaches 1 of f. So probably back here, maybe I should have said not 2, then why it's not continuous at 1.5. So again, we'll do the function value, the limit value, and the comparison of those at 1.5. So at 1.5, I'm getting a y value of 2.5 here, I would say. So lots of decimals in this one. And as we approach 1.5 of f, we do see that our behavior is pretty much the same from the right and the left, but that value for y is about 1.5. Well, the behavior at 1.5 does not equal the behavior sufficiently close to 1.5, which is the limit. F at 1.5 does not equal the limit as x approaches 1.5 of f. Okay, these values do exist, but they just don't equal each other. The type of discontinuity there is removable. All right, so down here, just once again, we're just going to invoke the definition of continuity and explain whether or not the function is continuous at the given value of a. So again, we know our sentence starters. I'm going to start with the function value at 1. And I'm going to get 2 over 1 squared is 1 minus 1 is 0. So immediately the function value does not exist. But we have to investigate further to see what type of discontinuity it is. So remember, if I do direct substitution on a value and I get a non-zero constant over 0, then that means as a limit, I can give it a positive or negative infinity. So what I'm going to do first, though, is factor and reduce, though. Just want to investigate about the vertical asymptotes. So when I factor the bottom, x minus 1, x plus 1, the x plus 1's divide out. So now I'm going to have a hole in the graph at x equals negative 1, and it's going to be removable because I have a limit. If I were to take the limit as x approaches negative 1 of f, I would get 1 over negative 2 because again, this reduces to 1 over x minus 1. So if I plug in negative 1, I would get 1 over negative 2 or negative 1/2. So that's where the hole would be located on the graph, negative 1 comma negative 1/2. What remains in the denominator is this factor of x minus 1, and that's where my vertical asymptote is going to be. So the vertical asymptote is at x equals 1, another point of discontinuity, but this kind is going to be infinite. So again, to answer the question, we have two types of discontinuity here. One at negative 1, which is a hole because the limit does exist. And because of a vertical asymptote at x equals 1, that's going to be infinite. Over here, The function value at 0 is going to be right here, so f at 0 is 4. But my limit from the left of 0 is going to be -3. While the limit from the right, well, 0 plus 1 is 1, and the natural log of 1 is 0. Minus 3 is -3. So my limit, as x approaches 0 of f, does equal indeed -3. But the problem is f at 0 does not equal the limit as x approaches 0 of f. So therefore, it's not continuous. What kind of discontinuity? Well, the function value does exist, and so does the limit. But the limit and the function value are not the same. So therefore, at 0, we would say that's a removable discontinuity. This one I'm not going to take us through because I think we know by now we have to write this as plus or minus x minus 2. And, at the value of 2, it doesn't exist. You get 0 over 0, so the function value doesn't exist. So if we were to, take the pains to rewrite this, this would produce a positive of x minus 2. This would be a negative of x minus 2. This gets the greater than. This gets the less than. I'll bring back my x minus 2 for each. The top simplifies to 1 for x bigger than 2. The bottom simplifies -1 for x less than 2. I obviously do not have a limit that exists because the values from the right and the left are not the same. From the right of 2, it's 1. From the left of 2, it's -1. But the limits do exist individually. They just don't equal each other. So the type of discontinuity here is a jump. And over here, f at pi is going to be equal to the cosine of pi. I need the function value, which is -1. But I could see that when I take the left-hand limit of pi, I put in pi and I get the sine of pi, which puts me here, -1, 0. That's where pi is. Sine is the y coordinate, so that value would be 0. So that means the limit from the left of pi is 0, while the limit from the right of pi would be -1. The limit from the left and the right do not equal each other, so that limit as x approaches pi of f does not exist. So the limit doesn't exist, but the limits do exist individually. So at pi, we would classify that as a jump. This is a very common question that's on the AP exam, is where we have to find the value of k, or some other constant. You can call it k, a, w, whatever you want, so that the function is continuous. So we want the value of the constant so the function is continuous. So in this problem, for the function to be continuous, the limit as we approach 1 from the left of f has to be equal to the limit as x approaches 1 from the right of f. And we need to communicate that using that precise notation. So I'm just going to substitute the 1 in for the x and get 2k minus 1. 1 in from the right for x and get 1. I'll just solve for k now. Add 1 to both sides, and 2k equals 2. Divide, and k is 1. In part B, if I have some room, once again, I have to take the limit as x approaches 1 from the left of f and set that equal to the limit as x approaches 1 from the right of f. And what's very important is here we have to communicate that using limit notation. In other words, this alone will not be sufficient for full credit. You need to communicate what you're writing using calculus. So I'm going to put the 1 in for the x, and I'll get 2 minus 1 minus k equals, and the 1 into here for x, be careful, is e to the 0, which is 1, times 2 is 2. So what does this clean up to be here? I think this is the homework where k had equaled negative or positive 1 a lot. If I subtract 1, what do I get there? I get 1 and divide by the negative, so I get k here to be -1. So again, I just substitute the 1 in, and I get 2 minus 1 minus k. Put the 1 in for the x. E to the 0 is 1 times 2 is 2. 2 minus 1 is 1. Subtract the 1 from both sides and divide by the negative. And I think this was okay over here, so I did get, you know what, I knew something was off. I'm taking a derivative here. Put the 1 in, and I get k minus 1 equals 1. That's a little different. I'm taking a derivative here in my mind. So I'm going to substitute the 1 in for the x and get k minus 1. and the 1 for the x down here, add 1 and get k equals 2. Okay. Down here, I'm going to, again, establish the limit from the left of 1 as a limit, and the limit from the right of 1. And now I can just substitute that in, -2 plus k, and the natural log of 1 is 0, and k equals 2 there. And down here, this is a little different. You don't have less thans or greater thans. So you have to set the function value at -1 equal to the limit value as we approach -1. So f at -1 is k. And then when I take my limit, I'm going to go to the top, which would be -1 squared is 1 minus 3 plus 2. That's -2. -1 plus 1 is 0. So I'm going to get here -2 plus 2 is 0 over 0. What am I going to do? Try and factor. So the top would factor into x plus 2 and x plus 1 over x plus 1. The x plus 1's divide out. So now I'm going to take the limit as x approaches -1 of x plus 2, which is 1. So k equals 1. Nothing much there really going on. This one sometimes gets, now you're like, well, why didn't you do that up here? Because the function value at 1 was the same as the limit value from the right. So I didn't need to do that. And down here, this would be the same case. You would set f at 1 equal to the limit as x approaches 1 of f. So where's f at 1 at? Right here. There is no x to substitute in. So that value would be 2k. But the limit from the right and the left better be the same. So hopefully they are. If I take the limit from the left, 1 squared plus 1 is 2. And down here, 5 minus 3 is also 2. So that limit is 2. So f at 1 equals 2k. And the limit is 2. So 2k equals, 2. So k is 1. And then down here, this was an old AP free response question. They like to do this where they give you a function up here, but they'll include it also down here. So g is this function consisting of f from -5 to -3, nothing more than that piece right there. Then we have a piece from -3 to 5. We're going to use the definition of continuity to decide whether or not g is continuous at x equals -3. Sentence starters: g, the limit, and the comparison. G at -3, the limit as x approaches -3 of g, and g at -3 in comparison to the limit. So where's g equal to -3? I think that's consisting right here, and that's into the function f, which I have to go back up in here. So 25 minus -3 squared, 25 minus 9 is 16, and the square root of 16 is 4. But we do have to show supporting work. So we have to take the limit as x approaches -3 from the left of g, and take the limit as x approaches -3 from the right of g. So from the left of -3, we just did it. We got 4. And then now from the right side, I substitute this in. I get 4 times the cosine of 0. The cosine of 0 radians is 1. Just know that. And 1 times 4 is 4. So my limit does equal 4. And this would be an incomplete response. We'd have to conclude, yes, it's continuous, because g at -3 equals the limit as x approaches -3 of g of x, which indeed equals 4. Okay, and that concludes the solutions to homework number 8 on the second part of definition of continuity.